Welcome back to Forge College. We are continuing our Advanced Testing with Foundry course, diving into performance optimization for smart contracts. In the previous lesson, we covered collecting and analyzing transaction flows. Now it is time to put that data to work. If you have ever waited for a bloated test suite to finish running, productivity gears grind to a halt. By applying targeted optimizations using the profiling data we gathered previously, we can slash test runtimes by 30 to 60%. We will also drastically reduce the gas overhead those tests consume. Speeding up your test suite directly protects your cognitive focus. By cutting out idle time, you stay engaged in solving problems, instead of staring blankly at a loading bar. Before changing a single line of code, we have to capture the current execution time and gas usage. We do this by running Foundry's gas report flags to establish a clear, quantitative baseline. This data table shows exactly where the time goes. We see specific slow test functions paired with high gas costs and execution times. The usual suspects tend to be heavy token minting loops, massive multi-step governance flows, and complex external Oracle integrations. Let's address those heavy loops. When a test repeats an expensive on-chain operation, like executing a token mint 100 times, we apply a technique called surface area minimization. We refactor these loops into test-only, deterministic helper functions. Instead of executing full on-chain mints one by one, the optimized code uses a helper like _seed balances to distribute balances by manipulating state directly. These helper functions must remain strictly isolated inside your test files. You want to manipulate state for testing purposes without polluting your actual production smart contract logic. Bypassing actual contract execution for test setup keeps your assertions completely valid, while entirely eliminating the unnecessary gas and time overhead caused by repetitive on-chain actions. Next, we address tests that require massive, multi-step global state setups. A good example is a full governance execution flow that requires proposing, voting, queuing, and executing. The vm.snapshot cheat code locks in the expensive setup state, avoiding recreating it for every assertion. From this locked position, you run multiple assertions consecutively. When finished, vm.revert2 instantly resets the board to our locked state, ready for the next test with zero overhead. Setup isn't the only source of drag. Real cross-contract external calls, like fetching prices from an Oracle, introduce unpredictable network delays right into your test suite. To fix this, you replace those real external Oracle calls with deterministic cheat code stubs or lightweight mop contracts. These stubs return fixed, hard-coded values instantly. By stripping out the network wait times, you eliminate both the associated gas costs and the unpredictable latency. Using snapshots and stubs converts unpredictable global state bottlenecks into isolated, highly predictable unit tests. Some complex integration tests simply cannot be mocked or minimized without losing their verification value. We still need them, but not every few seconds. This brings us to selective execution. By using a simple if statement to check an environment variable like fast test, we can explicitly gate these heavy, slow tests. In a practical workflow, you skip these heavy tests locally to maintain fast iterations. Then you keep them fully enabled in your continuous integration pipeline to ensure comprehensive coverage. Cautionary tone. However, we need to address the primary risk of test optimization: over-mocking. Over-mocking happens when your tests turn green and pass, but actually mask broken internal contract logic. Because you bypassed the real behavior with a mock, you might completely miss a critical flaw. The golden rule of mocking is simple. Always preserve at least one unmocked end-to-end integration test. This ensures the actual logic still matches exactly what your mocks are simulating. Raw test speed is only valuable if the tests remain valid. If your mocks hide bugs, you are simply failing faster, not coding better. Now it's time to verify the work. Run the exact same gas and time report commands from earlier to generate new metrics. This chart shows the clear before and after. We see massive drops, tests going from 18 seconds down to 4 seconds, alongside order of magnitude reductions in total gas used. In our next lesson, we will synthesize these techniques into a standardized continuous integration checklist. An optimized test suite requires continuous measurement and targeted refactoring as your codebase grows. It is a living asset that scales alongside your development. This lesson was made by Forge College. To learn more about this subject and explore other Web3 related topics, visit forge.college. Keep those tests fast, and we will see you next time.